Hello! In this video, we are going to prove the following theorem. Let a and b be real numbers. Then for all non-negative integers n, ab to the power of n is equal to a to the power of n times b to the power of n. Now, let's first remind ourselves of our definition for non-negative integer exponents. Let a be any real number. For each non-negative integer n, we define a to the power of n to be a real number, recursively as follows. So a to the power of 0 is going to be equal to 1, and a to the power of n plus 1 is going to be equal to a to the power of n times a for every non-negative integer n. So now, let's get into proving this theorem. Now we're trying to prove a statement about all integers n greater than or equal to 0. So we're going to prove this statement by induction on n. So we'll start with the base case. In the base case, we are trying to prove that this equality is true in the case where n is equal to 0. So really, we want to show that ab to the power of 0 is equal to a to the power of 0 times b to the power of 0. So let's write out the left-hand side. We have ab to the power of 0. Now, according to our definition, any real number to the power of 0 is equal to 1. So ab to the power of 0 is equal to 1. Well, then we can express 1 as 1 times 1. And any real number to the power of 0 is equal to 1. So we can replace this 1 with a to the power of 0, and we replace this 1 with b to the power of 0. And that's it. We see that ab to the power of 0 is equal to a to the power of 0 times b to the power of 0. So we've shown that this equality is true in the case where n is equal to 0. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0, and we assume that this equality is true. The whole goal of the induction step is to show that this equality is also true for n plus 1. So really, we want to show that ab to the power of n plus 1 is equal to a to the power of n plus 1 times b to the power of n plus 1. So let's write out the left-hand side, where we have n plus 1 here. Now, according to the recursive part of our definition, ab to the power of n plus 1 is just ab to the power of n times ab. But then, by our induction hypothesis, ab to the power of n can be re-expressed as a to the power of n times b to the power of n. So I'll re-express it like this, keeping it in parentheses. But now, we are going to manipulate this using the associative law and commutative law for multiplication. So applying the associative law, we can move these parentheses around b to the n times ab. And then applying the associative law again, we can move the inner parentheses around b to the n times a. And then applying the commutative law, we can swap b to the n and a. And then applying the associative law again, we can move the inner parentheses around b to the n times b. And then applying the associative law again, we move the outer parentheses around a to the n times a. So pretty much we have manipulated a to the n times b to the n times ab into a to the n a, b to the n b. Now, according to the recursive part of our definition, a to the n times a is just a to the n plus 1. b to the n times b is just b to the n plus 1. And that's it. Through this chain of equalities, we have shown ab to the power of n plus 1 is equal to a to the n plus 1 times b to the n plus 1. So we have shown that this equality is true, where instead of n, we have n plus 1. And that was the whole goal of the induction step. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. So really, by mathematical induction, we have proven for all integers n greater than or equal to 0, this equality is true. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.